In this video, we'll look at a brief overview of the binary search algorithm. In the binary search algorithm, the strategy is to halve the search space at each step by comparing the search value with the element at the middle of the search segment. Now, binary search, of course, takes advantage of the fact that the array that it's searching, or the space that it's searching, is sorted. If the space or the array isn't sorted, then you can't use the binary search algorithm. You'd have to sort the array first with something like selection sort and then apply the binary search algorithm. So in order to demonstrate how the binary search algorithm works, we're going to take a very small array of 10 items, 10 integer items, and we're going to search that array for a particular value. In this case, the key that we're looking for is the value of 22. Now we can see straight away that the value 22 is in the array. So in this case, a linear search wouldn't take very long to find 22 in the array, but we'll demonstrate how the binary search will work on this sample array. Obviously it will work much better, or be more efficient at searching larger arrays. So if you've got an array of 100,000 items, it's going to split that array in half straight away in the very first step, which is obviously a very efficient way of searching a space for a particular item. So in order to demonstrate how this works, we're going to use a number of different indices into the array in order to split the search space up. So what we'll do is we'll use a number of different index variables. So for example, at the beginning of processing, we'll use a variable j, and we'll set that variable equal to 0. We'll also use a variable k, and we'll set k equal to the size of the array, which in our case is 10. Now this represents a beginning state, a start state, and of course in that start state all of the items in here in that segment need to be searched. Okay, so this is our search space here, if you like. We need to search those items. So far we haven't searched any of the space in here. Now if we think of the end state will look quite different. So the end state will look a little bit like this. So we'll have our array again, let's call it f, and hopefully at the end of searching what will happen is j and k will move positions. So j will be here and k will be here, and hopefully the last item that's left between j and k in the search space will be the item that we're looking for. In this case we know that the value is definitely in the array, so we should end up with a situation like this. So j will move in this direction, and of course k will move in from this direction. So j will basically move to this position, and k will move from the end of the array to this position to give us this single item that's left in the array. And that will happen when j is equal to 3 and k will be at position 4. So when we've just got that one space in between the indices and there's only one value left, that's when we stop searching. So the guard on our loop will be while j plus 1 is not equal to k. And this is important to get that guard right, because we want to be left with one item. So we're saying, well, while j plus 1 is not equal to k, now in this case the guard will break, because look, 3 and 4, so we add 1 to 3 and we get 4, and of course 4 is equal to 4. So this guard is important here. J plus 1 not equal to k. and as long as we end up with one element left, then we will have probably found our value. But if this fails, if this becomes j plus 1 is equal to k, then the loop breaks and we're finished, and we'll check to see whether or not the value that we're left with, that single value that we're left with, is equal to the value that we're looking for. So in order to really see how this works, we're going to step through and look for our value. So remember, our key value, the value that we're looking for. Actually, let's write this down here a bit so it doesn't get in the way. So our key value that we're looking for is 22, and j is going to start off at 0, and I'll signify that by a yellow line. So j is here to begin with, equal to 0, and k, which I'll signify with a green line, starts up here, and of course k in this case will be equal to 10. So how do we proceed once we've got the values set to begin our search? How do we proceed? Well, we need to split the array in half, and to do that we use this little equation here, which I'll write in red. So we'll say I is equal to j plus k divided by 2. So this is going to give us an index I, which will be in the middle of the array, and this is how it works. If we look at the initial values, we have j equal to 0 and k equal to 10. So 0 plus 10 is 10. 10 divided by 2 is 5. So the very first index that we get in the array is 5. So I, which I'll draw in red, is positioned here. Now it's important to note that we're dealing with integers here, and when we have division and integers, we're only going to get back the whole number part. So this little equation here is only ever going to give us back the whole number on dividing j plus k by 2. So it's always going to give us a whole number index into the array, and we'll actually see that as we progress through the example. So I is now set at this position, which is 5. And what we do is we check the value at I, and we say the following. So we say if our key, so our key is 22, so if the key that we're looking for, which is 22, is greater than or equal to fi, then what we do is we want to split the array. We want to check to see which segment that we need to keep. So if the value that we're looking for is greater than or equal to 44, then we want to keep this part of the array from I to k. If the value that we're looking for is less than 44, obviously we would want to keep this segment of the array and throw away this piece. So we check to see if the value that we're looking for is greater than or equal to f.I. And if it is, we keep that segment. So in that case, we would want to keep this piece with k and I, and j would be here. So in order to do that, what we do is we say j is equal to I. So we move j up to I. Else, if the value that we're looking for is not greater than or equal to f dot I, what we need to do is keep the other part. So let's just draw a little example here again. So again, we have I here in the middle, we have k here, and we have j. So in this case, the 22 is less than fi, and in that case, we want to keep this segment. So what we do here is we set k equal to I. So we bring k down and set that equal to I, and in that sense we keep this part of the array. The opposite is true up here. If it's greater than or equal to f dot I, well then it must be in this segment, so we want to keep that segment, and in that case we change j. So really our decision is based on comparing the value that we're looking for with the value in the middle of the array, and then we decide which segment of the array to keep, and we have the array again and move on. So we'll step through this particular component of the search algorithm in detail here with our values in the array and see what happens. So let's just rub all that out and we'll step through and we'll see how those decisions affect the search. So as we can see, I, the very first position for I is 5. And the value at I is 44. So our comparison then becomes 22 greater than or equal to 44, and we know that 22 is not greater than or equal to 44, it's less than 44. So this means our value has to be on this side of I. So we want to keep this part of the array, the left hand portion. So in this case we change k and we say k equals I. So effectively k is equal to 5. So let's rub out our current position. So k is going to be equal to 5, so k is now here. It's moved from down there at the end of the array, and k is now 5. Alright, so what's next? Well, the next thing that we need to do is find the middle of this portion of the array. As you can see, in that one step, we've halved the search space. So we no longer have to worry about this portion of the array. Don't have to search it. Okay, so we find the middle of this portion of the search space and we use our little equation here again. So j is 0, k is 5, so 0 plus 5 is 5. 5 divided by 2 is 2.5. But remember, we're only going to get back the whole number part of that, so we only get back 2. So I is now set to 2, which is here. So now we have I equal to 2. And we look at the value at I, and we have 13. So now we do our comparison again. And we say 22, the value that we're looking for, is it greater than or equal to 13. So in this case, 22 is greater than or equal to 13. So what we want to do is keep this portion of the array. We can discard this bit at the start between j and I. We don't need that anymore because we know the value we're looking for is greater than or equal to 13. So in order to keep this portion of the array, we keep k where it is and we just increment j. We set j equal to I. So we set j equal to I. So now j is equal to 2. And we move on. Let's move j up here so we can see where we are. So j now moves from being at 0 to 2. So we have j now here, signified by the yellow line. So now j is here, and j is equal to 2. Oh, oops, not 5, 2. And we proceed. So now we need to find the middle of this segment. So we bring our equation in again. So now j is equal to 2, k is 5. So 2 plus 5 is 7. 7 divided by 2 is going to give us 3. So we can draw in our new I here. So I is now equal to 3. And we check our values. So now we say 22 greater than or equal to, and the value at I is 22. So what happens here now is we just, even though it is the value we're looking for, we still go through the process. So 22 greater than or equal to 22. Yes, it is. So 22 is equal to 22. So what we want to do is we want to keep this portion of the array. We can discard this bit. So again we say j is equal to I. So j equal to I will give us j equal to 3. And once we do that, we can move our values up here in our array. So I will move, and j will move. So now j will be equal to 3. And we do the same thing again. We say, okay, j is equal to 3, k is equal to 5. 5 plus 3 is going to give us 8. 8 divided by 2 is going to give us 4. So I is now at 4. And we look at the value here, which is 25. And we say 22 greater than or equal to 25. So is 22 greater than or equal to 25? No, it's not. It's less than 25. So in this case, we want to chop this part off and we want to keep that part between j and I. And to do that, we set k equal to I. So now k equals I, and k is now equal to 4. So let's move our values in the array. So I is now moved out of there, and k is now equal to 4. Let's draw that in green. So k is now here, k equal to 4. And now what we have is a situation where the guard on our loop will break, because the guard on our loop, remember, is while j plus 1 is not equal to k. And j plus 1 in this case, so j is 3, j plus 1 is 4, 4 not equal to 4 is false. This will break, our loop will end, and we'll be left with j set at the value 3, and that will be the value 22. And it's just a simple if statement then to check to see if the value that we are left with is the value that we're looking for. And of course, in this case, it is. So if we move over to our code window, we see that we've got a little template program here just to carry out our binary search. So I've declared an array, and it contains the same values as our little sample over here in our demo window. And I've also declared a variable x of type int, and that is going to be our search value, so we'll set that equal to 22. Now, for the purposes of this little code demonstration, we're going to write the binary search as a function. So we'll say public static, and it's going to return a Boolean value, and we're going to call it binary search. It's going to take an array as an argument, so we'll use our square brackets for that, and we'll call that array A. And then we'll also pass over a key to search for, so that will be an int, and we'll call that key. And the very first thing that we'll need to do is set up our variables j and k. So we'll initialize j and k. And remember that j, so we'll say int j, starts off at 0, and k is an integer, and that also starts off at a.length. So j is going to start at 0, and k will start at the size of the array. The next thing we need to do is write our loop. So we need to loop until we are left with a segment size of 1, until we're left with one item. As you can see over here, when we stepped through the process over here, we were left with the very last value in the array, which happened to be the one that we were looking for. So we want to be left with a segment of size 1, and the loop to do that will be while j plus 1 not equal to k. And inside the loop, the very first thing we need to do is we need to find middle of the search segment that we're dealing with. And to do that, we use our little equation. So we say int I is equal to j plus k divided by 2. And remember, this is integer division, so it's only going to give us back the whole number part of the division in I. Once we do that, we're now ready to check which segment we need to keep. And we do that by changing j or k. And we do that with an if statement. So we say if the key is greater than or equal to the item at the middle of the array. So I will give us the middle of the search segment, and to get the item at that segment we say ai. So remember, a was the array that I passed in as an argument. So if key is greater than or equal to ai, then we need to set j equal to I. So if the value is greater than or equal to AI, or whatever the middle segment is, we want to keep the right hand side because it's greater than or equal to that. So in that case, we shift j equal to I. We do the opposite in the other case. So if the key value that we're looking for is less than AI, well then we say k is equal to I. In that case, we keep the left hand side of the array, j stays where it is, and we set k equal to I, getting rid of or discarding the right hand side. Now that's basically the loop done. All we need to do after the loop is check to see if the element that we're left with is the one that we're looking for. So to do that, we can use an if statement. We just say if key is equal to aj, then we can return true, else we return false. So remember that j is going to be the index of the very last element in the array that we're left with. So between j and k is the very last element, so we look at aj to see if it's equal to what we're looking for. So we check to see if key is equal to aj. If so, we return true, we found their value, else the value that we're left with is not the value we're looking for and it doesn't exist. So that's basically the binary search written as a function, and we can use that function now to search for a value. So in our main method, we can use that. We can say if binary search, and we can pass over our array f and a key value to look for, so that's x, and I can say equals equals true. So the binary search function is going to return a boolean. I don't necessarily need the equals equals true here, but it can just make it a little bit clearer to see what's going on. So I'll leave it there, and I can say system.out.println we have found our value, and then else I can just print out a message opposite to that, so we can say we have not found our value, and we'll save that and compile, and let's run it and see what happens. So okay, we can see we have found our value. We've got the output that we were looking for. Now if I want to test this, I could just go back and set x equal to some value that I know is not in the array. So let's set it equal to 200, for example. We'll save and compile and run the program again, and as you can see, it outputs we have not found our value. So the binary search can be used on arrays that are sorted. It's really good when the array size grows to be something really big because it's a very efficient search strategy. It doesn't compare very well against linear search for smaller arrays like this. It's really just when the size of the search space begins to grow, and if it's sorted, then you can really utilize a binary search, and it will be really efficient at searching bigger and bigger spaces.